Can a robot really perform complex bicycle stunts? This paper shows exactly how it's done. Let's get into it. Let's start with the featured paper, Bicycle Acrobatics with Reinforcement Learning, by Shamal Fahmy and Gabriel Nelson from Robotics and AI Institute. Here's a full breakdown.
On the left, we see the trajectory of the bicycle performing a complex stunt, which is broken down into several distinct skills. These skills, like the flip shown in green or the waypoint following in blue, are each learned using different reinforcement learning approaches, such as motion imitation or goal reaching. Next, the system uses a policy orchestrator, shown on the right, to manage these individual skills. This state machine uses triggers, like time elapsed or specific events, to seamlessly switch between policies like flip and drive and create long, complex sequences. This method demonstrates high success rates across a variety of stunts, from basic maneuvers to complex orchestrated sequences. Many tasks, including driving and flip and drive, show perfect 1.00 success rates, while even the intricate kip, jump and flip stunt achieves a 0.97 success rate.
Up next, our second paper out of 3, DrawAI, Agentic Benchmark and Workflow for Making Raster Images Editable by Pu Chao and Lu Yang from Beijing University of Posts and Telecommunications. Let's break down its key contributions.
To start, modern AI can generate great-looking images, but they often come out as flat raster files like PNGs, which are hard to edit. Our core task is to take these raster outputs and convert them into fully editable artifacts, like the SVG or PPTX file shown here. To measure our success, we introduced DrawAI Bench, which you can see in this center panel. It evaluates how well the editable artifacts match the original image, using both rule-based comparisons and a rubric-based VLM evaluator for a comprehensive score. Feeding into this is our proposed method, DrawAI Flow, an agentic workflow for making these images editable. This workflow, shown along the bottom, is a two-stage process that begins with perception and planning before moving to the actual reconstruction. Next, let's look at the agents involved. The process starts with a parser agent. It analyzes the raster input using tools like element segmentation and text detection to create a detailed element plan. Finally, the reconstruction agent doesn't just write the code once. It uses an iterative loop to perfect the output. As shown in the code-native reconstruction box, it generates code, renders an image, validates it, and then refines the code until the result is accurate. The top-performing models, such as GPT 5.5 and Claude Opus 4.8, achieve excellent overall scores above 90 on the DrawAI benchmark. These leading models show strong fidelity across all categories and generally high editability, with some models like Minimax M3 exhibiting particular strengths in text editing.
Up next, our third paper out of 3, The Boy Who Cried Wolf, Adversarial Misclassification of Safe Inputs as Unsafe in Multimodal Guardrails by Shoa Shi and Sholing Ji from Zhejiang University. Let's break down its key contributions.
Let's start in the top left in the feature-based view. We take a normal, benign image and add a small, almost invisible learnable delta perturbation to it, creating our adversarial input. Feeding into this, the attack is guided by a process of semantic distillation. We calculate a distillation loss between the unsafe embedding from a harmful image and the adversarial embedding produced by our perturbed safe image. Next, to make the attack more robust, we align the attack with a general concept rather than a single instance. This is represented by the unsafe distribution, where we push the adversarial embedding towards a whole region representing a harmful concept like violence. The proposed USD method consistently achieves the highest ASRR, attack success rate for refusal, across all tested models, datasets, and perturbation levels. It substantially outperforms other methods like MLLM refusal, MFITT, and CoA, often by a large margin, for example, reaching 84.3 ASRR on VQAV2 with Llama, Guard 3 Vision at Epsilon 16/255.
Those were the top papers. Now let's zoom out. ArXiv received 1,481 new computer science papers across 73 subfields today. Here are the trending areas shaping the field. Zooming out, the day's research clustered into 5 big themes: robots mastering complex physical tasks, robust AI for critical applications, LLMs, diverse applications and efficiency, resource optimization for complex systems, self-improving AI agents memory. The full paper list is in the pinned comment below. That's all for today's ArXiv Computer Science Daily. If you found this helpful, please like, leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.